Thank you so much for having me here today. It's a little intimidating. At the first dark matter conference I went to, Leslie Rosenberg stated that Axions were the thinking person's dark matter candidate. So I'm here to convince you that WIMPs are still a viable option, and I'm going to do that with cartoons. So dark matter and WIMPs come up a lot in pop culture, and I took a little bit of a cue from the really awful book. I actually brought it with me to look at because I had it from my nephew, The Diary of a Wimpy Kid, which is a book in cartoons. And so we'll have a few cartoons spread throughout this. Of course, one of the favorite of us scientists and someone who likes to write a lot about dark matter is Randall Munroe in the XKCD, where he talks about dark matter being squirrels. So let's get started. Now, it's also a great time to be talking about these things because it feels like a really interesting time in the field. We've just come out of kind of 2 years of coronavirus pandemic, working from home, not getting to meet in person, as we've talked about. And so it's really exciting to be back and talking to other people. And while we're talking to other people, we're also doing lots and lots of roadmaps. So the European strategy for particle physics has ended. There's a European strategy for astroparticle physics. And what's culminating this summer is the US snowmass process. And so I should also state right now that you'll see my clear biases from my accent. I'm an American, but I'm now located in the UK. And I'm an experimentalist working on the LZ experiment. And so that'll tint a lot of the things I say. And so it's another reason that things are exciting is that the LZ and xenon n-ton detectors have been up and running for a little less than a year and have given us their first results that we'll hear more directly from other speakers about. But that means that there's new energy in the field that hadn't been there for a few years as these big detectors took a long time to build. And of course, the real reason, which is still really interesting, is that we haven't seen other very clear signs of physics beyond the standard model at the LHC. And so the open question of dark matter is really a greater fulcrum for the field of what is there to look for physics beyond the standard model. So I'm going to lean heavily on some of these reports. As I said, the European strategy, there's an APEC committee report and a number of reports in the snowmass system, so lots more information there. And I want to start off by telling you the messages I want you to get from my talk. And so flying in over the coast of the North Sea, this is the view from on high, that WIMPs and high mass particle dark matter is still a viable, motivated dark matter candidate. But it's not the only one. There are wider models of particle dark matter now that sometimes we wave our hands and are still calling WIMPs, and other times we're separating out. They cover broader mass and interaction strength parameter spaces that are also very well motivated. And we've got some really trustworthy technologies now that can go as far as we think they can before they start seeing nuclear recoils from neutrinos coming at us from the atmosphere and from the sun. And for higher mass dark matter, these are the liquid noble detectors. And when they get to a really big size, they're not just doing dark matter WIMP searches, but they can do other physics searches also in neutrino physics and neutrino astronomy. But these higher mass particles are not the only things we're interested in, as the first point says, and so there are brand new technologies coming online with many different detectors, many different collaborations to probe the lower mass particle dark matter. And when these technologies are proven at the lower mass range where we have more solar neutrinos, we should also try and get down to be seeing neutrino events in these detectors. And the most exciting thing to remember is that we're not trying to set limits. That's not what we want to do. We want to discover dark matter. And really, these detectors are set to be, at any point, we can find a discovery. And of course, it's going to be a slow process, right? These detectors run for many years. You're going to start with a handful of events. You're probably going to say, oh, we just have a little bit of a weak limit at first. And you might start to see hints in a very complementary set of experiments, not just in direct detection, but with indirect and collider searches as well. And all of those are going to be important. So for my brief outline, I'm going to talk still a bit more about those particle models before moving into how we do these direct searches and really what the state of the field is right now, before I talk a little bit more about what our plans and expectations for the future will be in the dark matter particle field. So when I first started giving dark matter talks, this was my theory slide. I said, oh, there's the WIMP miracle at 100 GeV mass, interactions at the weak scale. You then get magically a freeze-in of, you've got particles being created when the universe is hot and dense, and as the universe expands, it's no longer able to create those particles anymore. They annihilate with each other, and then they're far enough away from each other that they stop annihilating, and we get this freeze out. And that freeze out, if we use these numbers, would give us the density of dark matter of 0.3 GeV per cubic centimeter that we see now, and that's amazing, and that's a reason to look for this. And of course, even at the time that I was putting up this slide, we knew that that simple model with a Z moderator was not what was happening, but the other options for WIMPs fit in well with SUSY, which we were still looking for. The LHC hadn't turned on yet, and so we were looking for a lightest neutrino. So then people started to say these obvious things, which is haven't that true WIMP idea of the 100 GeV particle interacting with the Z boson been ruled out? And yes, they have. And isn't SUSY discredited since the LHC hasn't seen anything? Really, are we looking for a supersymmetric particle in this big detector that's the sole purpose detector? And so then I started to give this uglier slide where I hid the fact that there's just lots of models. They're on an energy axis, and again, XKCD says, haha, some of these models are really funny. And I'd point out that he mentions electrons painted with camouflage, no-see-ums, pollen, and bees, and space cows. So just saying, there's a wide range of models that you might think are crazy, but hey, we can look for them. Well, that's not what I'd like to show now. So still in the cartoon phase, here's a much more motivated picture of what WIMP dark matter could be. So we still have places where our thermal WIMPs, that freeze out model would be. We have models of the NMSSM, there's PMSM options left of still some supersymmetric models. We have asymmetric dark matter models where the reason for our antimatter asymmetry could be solved in the dark matter sector, and those models naturally arrive. At much higher masses, we have non-thermal dark matter where there are models that kind of arise out of inflationary theory that could create really massive particles that would be much more strongly interacting than some of the other models we're probing right now. But they'd be so massive, there wouldn't be a very large flux of them if we were looking for them. And then as we get to lower energies, there's strongly interacting dark matter, sterile neutrino options, and options where the mediators are going to be new physics, new mediators that we're not explaining with the Higgs mediator kind of fits in with the supersymmetric models and the asymmetric models, but we can have brand new Z prime bosons giving us a wide range of options to search for. So we can see that this is over many more ranges of energy and interaction strength than we've been showing before for the classic WIMP, and all of these would still generally be classified as a particle dark matter. And so sometimes when we're talking about WIMPs now, we're talking about this broader picture. So what's our status in evaluating that picture? Well, our status is still that we focused on the old WIMP, so we've now reduced our x-axis back to what we've been standardly looking at, and we've got our dark matter nucleon cross-section, spin independent on the y-axis. And this is coming out of the SNOMAS reports, and the end story is what's been the story, is this comic brought up in 2014. We're really excited about our detectors. We turn them on, and yeah, we haven't found dark matter, but we're the best at not finding dark matter yet. And if we saw something, we would trust our detector if we were to see it. And so the grayed outlines are limits that already exist, so they have a kind of a Nike swoosh, and we exclude the parameter space above and to the right by them, where the shape is led by the threshold of your detector on the low mass side, and simply the density of dark matter able to travel through your detector on the right-hand side. And what we want to do is push in two directions, down and to the left. And we're going to do those in two different ways. But both of these directions are going to encounter the nuclear recoils that are induced by neutrinos, the atmospheric neutrinos and the solar neutrinos. And we can see this for in xenon, where you would start to see your initial sign of a solar neutrino here. So very soon we should be seeing boron 8 solar neutrinos giving nuclear recoils in our detectors, and then where we could still have a 3 sigma discovery down to. Now this, though, is not enough of a cartoon. So this is the picture I want you to actually remember in your head. We've got our neutrino fog. The colors are funny. It's really in gray. Our already existing exclusion lines are up here in this whiter gray. And where we were just in 2013 was still orders of magnitude higher. Our operating detectors give you this light blue line. And we're planning these detectors to get down into the neutrino floor. And we'll need new technologies, especially ones that are neutrino insensitive or discriminating against them, to get further into that neutrino fog. So this is the picture of what our field is at right now and where it'll be in the next few years. And we can look at this in other ways. We can look at our lowest points of limits for multiple detectors here, really dominated by the liquid argon and liquid xenon noble detectors. And there's an arrow coming down with a rate of increase that's improved over Moore's law for silicon improvement. So our detectors, we turn them on and we get an order of magnitude better with an order of magnitude larger detector. We're reducing our backgrounds. And this has been a fairly smooth transition, really held up by funding more than by technology for these scales. So how do these detectors work? Well, the liquid noble time projection chambers are a really elegant piece of technology. They're designed as a right cylinder, so the width is the same as the height. And we've got a lot of the liquid noble, so it's able to self-shield against external backgrounds. We generally choose xenon, which has no long-lived radioactive isotopes, and underground argon, which doesn't have the argon-39 isotope in it. And what happens is if a particle comes in and interacts, we get an initial flash of light. We detect that with photosensors at the top and bottom. We call that signal S1. We're not that creative on this one. And we have a large electric field. We drift electrons up to the top. We actually use a two-phase detector, usually pop them out of the liquid into gas where they undergo electroluminescence, give us a bright signal. That's our S2, and this actually lets us count the ionization electrons. So even though it's a light signal, it's counting the ionization. And then we can use this ratio, or the relationship between that S2 light and our S1 light to give us particle ID and discrimination against our most common electronic recoil backgrounds. So we use a deuterium-deuterium generator to create neutron single scatters in our detector, and it populates this band shown in red. And we can use the tritium decays to give us beta decay electronic recoils that populates the band up here, and that's where most of our backgrounds are going to be. And most of those backgrounds are going to be radon, krypton, and then a limited number of gamma rays from the surrounding materials of our detector. Eventually, we will also be seeing the electronic recoils from the solar and atmospheric neutrinos also. In argon, the S1 light actually has a timing structure to it, and it also has pulse shape discrimination then to give you additional abilities to remove electronic recoils from your sample. But it's still useful to see the TPC structure because of its excellent position reconstruction to be able to tell if there's multiple scatters. So the LZ and xenon n-ton detectors look very similar. So here's LZ's TPC. Here are schematics of what they look like. They're inside water shields and vetoes against muons and things to capture neutrons that could have singly scattered and looked like a WIMP inside the detector. So here's xenon n-ton at ground SASO. These are those example waveforms of an S1 and an S2 pulse. And shows where we get that XY position from that S2 light, and the timing between the pulses tells us the depth in the detector. And so these are two sensitive detectors with new results. There will be talks Tuesday and Wednesday by other speakers, but I'm sadly going to steal their thunder to tell this whole story, which is that, so LZ has leading limits from just an initial run really set to say, like, we know what the status of the field is, we know how long we'd have to run to have a similar exposure, let's check out our detector. And so the LZ limit now is at, I think 5.8 times 10 to the minus 48, where we really had a downward fluctuation in our backgrounds that gave us this. We spent a long time understanding that. And xenon n-ton has done an amazing job with their electronic recoil backgrounds. And they had a big motivation to do this, which was their xenon 1-ton result. Their backgrounds are shown here with the background model in pink, and there was this excess. And their new result from the xenon n-ton detector, you can see, is low, and they expect to actually be able to turn on additional radon reduction systems to bring this down maybe by another factor of 2. So really impressive background removal. The LZ current backgrounds in the electronic recoil region are superimposed on this plot. And you see we don't have a flat spectrum, and that's because LZ's xenon didn't go straight into the detector after being underground a long time, but it had been decryptonized and then traveled above ground and actually through the Rockies. And so there was cosmogenic activation that gives us argon-37. And so this argon-37 creates a peak very close to where the xenon excess had been. So that makes it, we can see that it would be in tension with that result right here, especially when we show you what our time decays are too. But really, xenon n-ton did an amazing job in handling this. So how they did that amazing job, hopefully you'll hear in future talks. And the implications of these amazing backgrounds become of interest to the Axion community, because now these detectors can probe interactions with electrons and the electronic recoils. And that gives them sensitivity to solar axions, to axion-like particles, to dark photons, and to the neutrino's magnetic moment. So these detectors really are probing these other areas of science too. So moving from xenon to argon, the Deep 3600 detector is the first ton-scale detector operating. It's a single-phase liquid argon detector with its cartoon right here. And so it has 2 pi coverage of photosensors. It has to have large acrylic light guides between its PMTs and its detectors, because their technology of PMTs and argon itself make a bad match for neutron backgrounds. And so we block it with acrylic. And unfortunately, they couldn't fill the entire detector because of a cryogenic issue right at this difficult part of the detector called the neck. So Deep 3600 has placed limits, has placed additional limits in other interesting science. So effective field theory frameworks where we don't just talk about spin-independent interactions, but list all the possible mathematically feasible interactions with the nucleus and look at all those operators and all of the nuclear response functions and place limits separately in that way in a more complete manner. And they've also studied really Planck scale dark matter, which would give a really crazy multiple scatter bright signal that you have to really create an extra search for, otherwise you would maybe say it was a muon going through. But more exciting is that this summer, they're doing some hardware upgrades, which will allow them to fill their argon up to the neck, which will make their detector a lot easier to analyze. And they are also adding the ability to tag surface events in that area where they don't have as much light collection to find the surface alpha particles that could be there, as well as filtering dust out of their system. In the argon field, there are, as I said before, some time projection chambers, and they were the dark side 50 detector and the under construction dark side 20K. And these detectors have been very sensitive. Again, we see that same S1 and S2, but we see the difference in a wide S1 versus a narrow S1, the differences between our electronic recoils and our nuclear recoils. They are using the underground argon that reduces the argon 39 by a factor of 1,400 or more. And they're working on prototyping silicon photomultipliers for dark side 20K to not have that neutron problem from the borosilicate glass in PMTs. So we're started at these kind of highest masses of dark matter options where the liquid nobles do the best. You could also use bubble chambers such as the Pico detector. And then we're coming down now in mass and thus in recoil energy to other materials. So the next are the semiconductors. And very much borrowing Raymond Strauss's IDM slides, we're looking for detectors in cryogenic bolometers where there's an interaction in a crystal now, and you're going to find the temperature of that. So we're now seeing the full phonon energy, not just ionization or scintillation energy. And so you can get to much lower recoil thresholds and thus lower masses when you can collect the full phonon energy. And so there's a number of different detectors that are doing that. The Edelweiss detector using germanium uses NTD sensors. Crest Super CDMS, Casinus, and some Edelweiss are using transition edge sensors. And again, there are lots of interest in ways to discriminate your backgrounds. Here, we're primarily interested in surface backgrounds versus bulk backgrounds. And the detectors start running into problems, again, with cosmogenic activation and tritium that ends up in their silicon crystals. So these are whole new technologies that allow us to get to that lower end of the spectrum, but also, if we start looking at electronic recoils in any technology, we can get to a lower energy. And this is the idea of the Migdal effect. So our projectile comes in and hits our nucleus, and because our nucleus then gets offset from its electron cloud, one of the electrons becomes ionized. And we now have something that looks like an electronic recoil, but it really came from a nuclear recoil. And this allows us to get a signal at lower thresholds than we usually can, because this ionization energy is much easier to see in most of the detectors. Now, this is essentially just a theory right now. So there's multiple groups with separate experiments and with calibration sources in their current detectors trying to prove and calibrate this so that even though we're publishing results using this effect, they are uncalibrated results, and so they have to be taken with a grain of salt. So the Super CDMS detectors, again, this is showing my American bias, will be running at Snow Lab, and they have a somewhat complicated story of their detectors. They're going to have 4 cryogenic towers of detectors, some with germanium, some with silicon, some operated with their interleaved high ionization signal and phonon signal detectors, and some with a voltage applied across the crystal to let them amplify their phonon signal by the Luke-Neganov phonons and creating an extra ionization signal. So again, to bring low energy events above threshold. And so that will give them, so their lowest threshold and most sensitive detectors will come from the silicon high voltage detectors. Silicon because it's a lighter target nucleus than the germanium. and the high voltage because we're amplifying the signals. But so that's kind of where we are in the field right now. So a lot of the more interesting results coming from the lighter mass dark matter searches are still to come. But we're already planning what we're going to do next because it takes that long now in the field to do that. And so from the xenon point of view, the LZ and Xenon, N-ton, and Darwin collaborations will be joining together to propose the currently named XLZD experiment that would get fully into the neutrino fog over the mass range where the xenon detectors are sensitive. So such a detector could maybe turn on 2028, probably more like 2030, but fully cover the parameter space that's available for us to search. But when it does that, we actually will have still more science we can study. Again, as I've said, from our electronic recoils, we've got more dark matter signals to look for. We can study the neutrinos that we're going to be starting to see in our detector in both nuclear recoils and electronic recoils. We can wait and hopefully catch a supernova neutrino. I was 6 years old. My birthday is February 23rd for supernova 1987A. And now that I've been in this field for a longer time, you're like, oh, wow, you know, these supernovae should go off in our galaxy every 20 to 50 years. We've been waiting a while. And you know, hopefully one of these detectors, and many of these detectors are going to be on both in the neutrino field and in the dark matter field to collect these signals. And I think that's maybe the benefit of getting old, is that there's going to be, hopefully, something we can see. In the xenon detectors, we've got the ability to study the xenon 136 and xenon 124 isotopes that have neutrinos double beta decay or double electron capture. You can also dope an argon detector with those isotopes if you wanted to study them. So there's a lot of science we can do. It's not just this single WIMP idea anymore. And again, the very similar story was already being worked on by the argon community. So there was the Darkside 50 detector, the Mini-Clean, ARDM, and Deep 3600 detector that are coming together to work on Darkside 20K. And that would be a current generation detector under construction now. And then the Argo detector would be able to get to the neutrino fog in the argon field. So when we look to the future, one of the biggest questions left to us is again showing my bias, and we said we haven't found dark matter, except there is one detector that has consistently said it sees a signal. And so at the IDM conference this summer, new results from the Dama Libra Phase 2 detector have come online, showing an annual modulation in their lowest energy bins. And in fact, they're working on lowering both of their hardware threshold as well as their analysis threshold to continue studying this down to threshold to see if it flattens out. And so this signal of annual modulation would come because the Earth is traveling around the sun, which gives us a preferential direction with respect to the random dark matter halo. And so when we're moving into that wind, we'll have a higher added velocity together and could see more events over threshold than we're moving away. And so this is why there's dead bugs on the front of your windshield and not on the back of your windshield. And so, but this signal has not been seen in essentially any of the other detectors. And so this detector is a sodium iodide crystal, and it makes you start to wonder, is there dark matter that is preferentially interacting in these detectors? And so a number of other sodium iodide detectors are coming online to investigate this, currently running are Anais and Cosine. Sabre is in an early stage, and Cosinus will be coming online in the next year or two with much better lower background sodium iodide crystals that should let them really understand things much better, and most interestingly, start to have discrimination between electronic recoils and nuclear recoils. Because maybe the expectation in the rest of the field has been that these are background electronic recoils somehow that are environmental related to the laboratory. And so you have to run at the same lab with the same type of detector and hopefully have this discrimination to really disprove this, which is at an amazing 13.7 sigma, saying that it's not a flat background, that it's seeing this periodic structure. So then we get to the most cutting edge, newest technologies, of which I've only thrown up a smattering here so far, the ones I could find cartoons of. And again, we've got, now instead of using silicon in the Edelweiss and super CDMS kind of large crystal size, we're utilizing it in CCDs, and we're able to really see the ionization signal. We're seeing interactions potentially even on the electrons themselves. And so the DOMIC and Sensei experiments get together, and then the Oscura detector. So this would be able to reach the neutrino floor at the lower masses with just 10 kilograms. So, you know, we're a decade away from such a detector, but these technologies are proving themselves. Some other technologies, the NEWS-G detector is a gas ionization signal where you just have a single anode and the ability to see a signal anywhere in your gas target. We've got the PICO bubble chamber, and that collaboration has also morphed into the scintillating bubble chamber group, which would use liquid argon as its detector technology, which with a scintillation light like that same S1 light in the liquid noble TPCs, but with the bubble chamber technology where you're insensitive to electronic recoils, most electronic recoils, these detectors could get down again to the neutrino floor for most of the low mass region. Now, a lot of these detectors are also starting to use helium as part of the Tesseract collaboration and in the Quest DMC experiment, as well as other cryogenic crystals. And these technologies are also, maybe at least just for funding reasons, often linked with the Axion searches because they're really relying on quantum sensors and really pushing the quantum limit of their devices to reach their thresholds. And so this is a very exciting field because people have a lot of new ideas. We're hoping that more of them come to fruition and give us things to look at, but also because these have clear, implications for other technologies and quantum devices and quantum technologies, and that's a good thing for our field. Now, I've been talking primarily about this particle dark matter, but it's become really clear that we're not in separate communities. We're really all looking for this physics beyond the standard model that can explain the dark matter of our universe, and there's a great deal of complementarity. So this is taken from the snowmass process, which has some of the funny snowmass words on it, but we had particle dark matter, wave-like dark matter, and the ability over all of these regions, but to go out to higher masses with the cosmic probes of dark matter. And so we see, multiple different types of detectors that we can run over these large mass ranges where you can find dark matter. And we can see where the cosmic probes themselves, so studying things like the numbers of dwarf galaxies within the Milky Way that are going to be studied with the LSST Vera Rubin Observatory. Information, so that's the structure formation and ability to look for lensing candidates and seeing how many really compact objects we otherwise lens also will tell some of these stories. And so this gives really the final best cartoon that I'm really excited has come out of the snowmass process that links together particle dark matter and wave dark matter along with people doing indirect searches and cosmic probes. So we've got our dark matter mass still along our x-axis, but instead of leaving it as a number line, we're now indicating some amount of interaction strength, which is getting the extra air quotes because these aren't all the same interaction, right? Some of these are interactions with nuclei, some of them are with electrons, some of them are annihilation cross-sections, but this is some sense of the strength of how big a detector, what are we going to have to look at to find it? Where at the top our strengths near the standard model, and at the bottom is gravity. And the open parameter space for us, we have kind of the classic WIMP idea shown here in this oval, the thermal dark matter of any of those broader classes shown around it. We then have those dark sectors where you have a much more variety of mediators and particles. We've got sterile neutrinos. We then go to the axions, where we've got really a flat field of possible axion options that I'm sure you all know better than I do, along with a bright hint of the QCD axion. And then complicated dark matter sectors that would only be visible to the cosmic probes. So this is the landscape from the theory side. And this is where we are and what our current sensitivities and limits are from all of these different types of probes. We've got, in green, the cosmic probes. Our dark matter limits are shown here. The axion current status is here. And what's really exciting is if we delve deep and search wide, this is where we could be in about probably 15 years or so. Really, how much of this space of the classic WIMP and the QCD axion we could be trying to cover, along with improvements from the cosmic probes. So that brings me just back to my same conclusions. This was a lot of text, that's why I gave it to you at the beginning. The end message of it all is that we want to delve deep, go deep into these particle dark matter options, go deep into the QCD axion, but also search much wider, these much broader array of options, and that's going to be our best way to find dark matter. So, thank you.
Thanks so much, Kimberly, for this very interesting talk and also being perfectly on time. The talk is open to questions.
You have shown for a while the WIMP zealous with each cross section, but there you must have some limits or not, or some exclusion.
This is, it starts running into,
Yeah,
exactly,
right.
but right now it's not as excluded. We think, we think that would be one of the areas we would be excluding more fully later, but right now it's, a little bit has been excluded, but not all of it.
We're sitting quite close to a graveyard, so I hope my question doesn't seem really inappropriate. Is there a well-defined endpoint for these things? Is there some point at which you decide this is a better idea we go to something else?
So, it depends who you ask and what your precise level is. So as an experimentalist, I have this view that the theorists can come up with a new idea. If we keep not finding dark matter, they can keep telling us we could keep searching, is what it feels like to me. But that's a little bit more the case on the higher mass side. On the lower mass side, there are some much clearer, really, benchmark models where if we get to the neutrino fog, it might not be worth continuing to search at those lower masses, that they become much less motivated there. So that's what I hear from theorists. Again, that's what they say now. In 10 years, are they still going to say that? I think that that's why we want this very interconnected study with the other cosmic probes, with collider searches. Oh, something happened? Yeah. With things from gravity waves, with the lepton universality tests from like the G-2 experiments and LHCb, all of these I think will tell us more, hopefully, that we're not going to keep doing the same thing infinitely long. And that's maybe why there's an excitement that if we do all of these things, it feels like we should see something somewhere. I don't know if that answered your question enough, but.
All right, more questions?
I can do that. This could potentially be a relatively large question, but you can go for it to answer if you want. Can you just elaborate on what the role of the argon experiments is? It seems to me liquid argon is just worse inherently
So I think that in it taking longer now, that they had delays earlier in the technology. Right. So I started on an argon detector that literally never took data. When that happens, the whole field is hurt, but the technology itself isn't fundamentally limited. It doesn't have the spin-dependent sensitivity, but it does, but that's almost a good thing if you saw signals in both cases. I do, some of the ways that I very personally think about it is clearly, we want to be ready with another technology to confirm a detection if anybody sees something. And so the only other viable high mass option is argon, so we want to make sure that there's a viable technology for that. And we don't yet know if our plan for a xenon detector will really happen. We're in this weird phase where we're not too worried right now, but basically for the next 2 years, xenon is essentially unobtainable because of the war in Ukraine. And since both LZ and Xenon N-Ton purchased their xenon, a new use of xenon has come into the market, which is silicon chip lithography. They actually use the 178 nanometer light from the xenon scintillation. And so now there are people with bottomless pockets buying up the world's supply of xenon. So if we can't work out deals, which we all think are really going to be feasible and the market will respond to this need, because essentially you get xenon just from liquefied air, and a very limited number of plants right now get the extra rare gases. It's also linked with krypton, which is used for satellite navigation boosting. Like they emit krypton out the back and they move forward as a rocket. And so we think that'll happen. But if it doesn't happen, then maybe argon is our only bet. So that's why it's so worth it. So a technology that I decided not to fit in here at all is directional detection, where we're primarily still using gas TPCs, where since your dark matter wind comes from a preferential direction based on the time of year and time of day, if you saw a statistical number of events that you could see like a full head and tail of which direction your scatter happened, you could tell the difference between it and an atmospheric neutrino. That might be our best way to get down into the neutrino fog, but they're working currently with, cubic meter detectors, where their next step is a 10 cubic meter detector. And for the masses, we were talking about detectors that have to be more than like 100 tons, and 100 tons of like low pressure gas is going to be like literally cathedral sized. But there's still a large number of people in the field working on this because it's what we think is our only viable option in 15 years or so. So I think the argon, to me, fits in the same story, but that's still a really motivating reason to have it.
Okay, thanks. Let's take the last very quick question from York.
On your argon slide, you have these flat scale multiple scattering objects. What's the signal, and is it specific to argon, or is it something you could also see as it's
No, we could see it in all of our detectors. Really, really, the argon community had, with this Deep 3600 detector that wasn't performing as desired, they said, what things have people not put out papers on so we can be world leading? And so they're the people who realized we could do this, but other large detectors could do the same. Yeah.
All right, well, thank you very much again.